Thank you. Thanks for the introduction. And thank you all for coming. In terms of time, should I be shrinking my talk, or are we still on?
We can try to keep it as the original.
Okay. So again, thank you all. Over the past year, I've been working with my colleagues on thinking about network functionality in data centers. And this talk, I want to give you an overview of the work, and I want to finish with some open questions that we've encountered. In terms of time, I will try to finish 5-10 minutes before my slot so that I can get some feedback and we can have some discussions. So over the past decade, there's been a lot of innovation in network functionality for closed environments like data centers and enterprises. I'm going to use the term network functions to refer to this. This includes what you typically consider management plane tasks, things like load balancing and quality of service and security. This also includes data plane tasks, things like congestion control and scheduling of network traffic. Finally, it also includes application level tasks, things like selecting replicas based on application level information. So there's a lot of diversity here. Despite this diversity, we note that 3 common requirements underlie a lot of these network functions. First, they need to maintain state at the data plane. Second, they need to perform computation at the data plane. And finally, they need visibility into application semantics. Now, this last requirement is particularly important because a lot of network functions are best expressed in terms of application level messages. I'll explain what I mean by that with the help of a couple of examples. So the first example is flow scheduling in data centers. Over the past 3-4 years, there have been a bunch of proposals for improving application performance in data centers through careful scheduling of their network traffic. The goal here is to minimize flow completion time, and these solutions typically devolve to some variant of the shortest job first scheduling strategy. Now, for the sake of our discussion, I'm going to focus on the latest and greatest in this line of work. It's a solution that appeared at NSDI earlier this year called PIAS. And PIAS tries to reduce flow completion time, and the basic idea is very simple. When a flow starts, it's marked as belonging to the highest priority, and as it sends more bytes, it's gradually demoted to lower priorities. Simple idea. Now, let's think about the network function underlying this PIAS technique. For the sake of our discussion, I'm going to ask you to sidestep the question of where this functionality might be implemented. Going back to Marco's slide, it could be at the end host, it could be at the switches, or it could be at a middle box. Let's forget about that. Also, the original PIAS paper talked about scheduling of network flows. But we can easily generalize this, and we can think about scheduling of network messages, where a message is an application data unit. For example, if you have an application which is accessing a storage server, a message would be a read or a write or a create or any other I/O operation. Now, here's a pseudocode representation of this PIAS function. And I know code on slides is always tricky even at a PL venue, but I'll try my best to explain what's happening here. So this function takes as input a packet which is annotated with information regarding the message it belongs to. Now, first we check whether this packet belongs to a new message or an existing message. If it belongs to an existing message, we look up the past size of the message. That is, how many bytes that we have sent for this message in the past, which in turn dictates the packet's priority. Finally, we mark the packet with the right priority level and send it out. Now, the thing that I actually want you to take away from this slide is that this function is using application semantics. For a given packet, we need to know the message it belongs to, and that by definition is application level information. Second, it's keeping data plane state. For all current messages, we need to track how many bytes they've sent in the past. And finally, we're performing simple data plane computation. So the 3 requirements that I mentioned earlier. Let's do another example. So this example is data center quality. Yeah, sure.
Just a quick question. Can the application decide what it means by size? So HTTP versus DNS, 2 very different notions of size.
Yes.
Can the application vary that, or is the system deciding what it means?
No, the application can vary that.
Right.
One of the key challenges was how do we define that interface between the application and the network management layer so that applications can decide what difference means or different things mean without the interface being too broad.
Got it.
And we have made some design decisions, and it would be great to get some feedback regarding, we think they're the right ones, but some feedback would be nice.
Good.
So as we go into details, I'll tell you
Perfect.
what applications can express. So the second example, and of course, by the way, please feel free to ask questions, as in the questions are great, it's a nice, cozy audience, and there are two different communities, so I might have made some assumptions about what I make at a typical networking audience, which may not hold true. So please feel free to ask and modulate the level of information accordingly. So the second example is data center quality of service. It's a topic near and dear to my heart. There has been, it's a hotbed of research. And there have been a bunch of proposals for ensuring bandwidth guarantees across shared resources. This particular example is about quality of service guarantees across a shared storage server within the cloud data center. We have two tenants, red, blue. A tenant is a user who's renting virtual machines. And today, there's no performance isolation, which means that the red tenant can cheat. He can act aggressively, and he can get a greater share of the storage server at the expense of the blue tenant. Now, last year at OSTI, we had proposed a solution which entails offering each user with its own private virtual data center, which decouples your performance from what other tenants are doing. Without going into too many technical details, it essentially relies on two main ideas. First is per tenant rate limiting inside the hypervisor. And second is rate limiting of requests based on their actual size. For example, if we have a write operation, we rate limit it based on the request size. But if we have a read operation, we rate limit it based on the response size, because the read request is just tiny. It's a fixed size packet. Now again, here's a pseudo-QoS representation of the VDC functionality. Again, we have a packet as the input, and it's marked with the message it belongs to. And we are checking if this message belongs to or is a read or a write. And depending on whether it's a read or a write, we do the right kind of rate limiting. Again, the thing I want you to notice is we are using application level semantics. There is state at the data plane in terms of these per tenant queues. And finally, we are doing this computation on the data plane. Actually, we did this exercise for around 15 odd network functions, both systems in production and research systems. And in almost all cases, these three requirements kept popping up. Now, given this backdrop, let's think about how we do network management today. And Robert's slides are very helpful today because the state of the art is software-defined networking. Now you all know, well, most of you knew that already. This allows you to program the networks based on a high-level policy. And very briefly, the API, as Robert mentioned, between the data and the control plane is OpenFlow, which introduces this match action-based programming model. So you can match based on packet headers, and you can apply from a predefined set of actions. Now, this is a limited computation model, which makes perfect sense given the limited capabilities of switches. However, enforcing network functions at switches and the restricted nature of this API is not a good match for the rich functionality that we want to implement in data centers. You can't have state on the data plane, computation is very limited, and at switches, you don't have visibility into application semantics. By contrast, end-hosts are a very nice or a very natural enforcement point for these network functions. By their very location, they have good visibility into application semantics. For example, at the end host, you can observe OS events, you can observe socket events. You may even expect applications to participate in the management process and give you information that can be useful for implementing the network function. End hosts have more processing and memory capabilities, which means that presumably you can keep state and computation on the data plane. So these are the three requirements that I mentioned earlier, and end hosts are very good given those requirements. Beyond these benefits, there are other advantages too. enforcing network functions at end hosts leads to a natural partitioning of the enforcement overhead. Each end host is only responsible for the flows it is sending and it is receiving. Similarly, when you think about consistently updating network policy and consistently updating network functions, that's a tricky problem to solve when you have distributed enforcement across a set of network switches, but it's a much simpler problem when you have enforcement at end hosts. Now, I'm not claiming this is a panacea. Right, there are some network functions that are resource intensive and they require hardware support. There are some environments like ISPs where end hosts are not trusted. However, in closed environments like data centers and enterprises, we found that a large fraction of network functions can be efficiently and flexibly implemented at end hosts. Now, I want to point out that this is not a new observation, as in there have been a bunch of production systems and there are a bunch of research proposals where end hosts actively participate in the management process. For example, on the research side, Colin's work on end to the middle would be a very good example. On the production side, there is, I guess the most practical example would be the movement of the end hosts to the SDNs, which is what Open vSwitch from the Nicira guys is doing. I'm sure there are lots more players. Azure has something similar called VM switch. And the basic idea here is that you move the switch functionality. Earlier, the controller was programming these switch elements, is now going to be programming the end host hypervisor. Now, the programming API here, in most cases, is still OpenFlow or OpenFlow-like, which makes perfect sense given a lot of practical reasons. However, it also doesn't make sense. Because at the end host, you have all these extra resources, you have all this extra information, and you are still shackled by that limited computation model. As a consequence, a lot of the functionality today is implemented either on specialized brittle boxes or on custom kernel drivers. Also, in order to derive application information, developers typically resort to techniques like deep packet inspection. So effectively, you're looking inside the packet, inside the application part of the packet, to reverse engineer application level semantics, which is clunky, it's inefficient. And all this led us to the question, can we do better? So over the past year, we've been working on Eden, which is an architecture for enabling network functions at end hosts with minimal network support. Now, before we dive into the details, I want to quickly point out the two main ideas underlying Eden's design. The first idea is programmable classification of application messages. And this is based on the observation that most network functions are best expressed in terms of application messages. Here, a message is an arbitrary application data unit. For example, if you think of an application like memcached, which is a popular key value store, a message would be a get or a put. And a class refers to the set of messages to which the same functionality should apply. For example, in our memcached example, we may say that all gets should belong to the same class because we want them to achieve one kind of behavior, and all puts belong to another class because we want them to achieve another kind of behavior. So effectively, what classification is doing is that it is elevating applications to be first-class citizens in the network management process. The second main idea is a programmable data plane with a richer API. As I explain later, we are still adopting a match action-based computing model. However, instead of being limited to a predefined set of actions, we are allowing for arbitrary action functions. What this means is that you can have computation on the data plane, you can have state at the data plane, and this allows us to implement dynamic stateful policies. Now, here's the architecture diagram from Eden. I know it looks busy, but it's actually pretty simple, and I'll explain it piece by piece. So Eden comprises of three main components. First, we have a controller which provides global visibility. So this is based on the standard SDN observation that a lot of network functions can benefit from network-wide visibility. Second is Eden compliant applications. And not all applications need to be Eden compliant, by the way. And we call these Eden compliant applications stages. Stages can choose to classify their network traffic. And what that means is they can identify this is what I mean by a message, and this message belongs to this class. And this classification behavior can actually be programmed by the controller through the stage API. The final component is the enclave. So the enclave is the point along the network stack where we are actually implementing or enforcing our network functions. So think of this as extending and replacing the functionality that the vSwitch offers today. And again, the enclave can be programmed by the controller through the enclave API. And the enclave API is essentially a richer version of the OpenFlow API or OpenFlow-like APIs that's the state of the art today. So over the next few slides, I'll dive into the details of how stages and enclaves work. There's been a lot of work on controller design in the SDN context that applies here, but I'll come back to some of the open questions that pop up when you start thinking about the Eden controller towards the end of the talk. So first up is programmable classification. In Eden, applications and libraries and services can choose to classify their network traffic. This is based on the observation that while the enclave operates at the granularity of network packets, most network functions are written at the granularity of application messages. So there's a disconnect, and classification allows us to bridge this disconnect. Here, I'm showing what a classification rule looks like. So on the left, we have a classifier, which is a regular expression that identifies all messages belonging to this class. And the output of this classification process is a class name and metadata that should be associated with all messages belonging to this class. To make the discussion concrete, I've given a few examples of the classification capabilities of 3 stages. So the first line says is we've taken a memcached stage and we've made that Eden compliant. And that memcached stage can classify its traffic based on a 2-tuple comprising of the message type, that is whether the message is a get or a put, and the key being accessed. Remember that memcached is a key value store. And for each message generated by memcached, it can associate metadata comprising of a unique message identifier, the message type, the message key, and the size of the message. Similarly, the HTTP stage might do a different kind of classification, and even the Eden enclave can do classification based on the standard IP5 tuple. What this means is that we can implement policies that you would typically achieve today using something like Open vSwitch. Now, the controller can interact with these stages through the stage API. So the controller can query a stage and it can ask to determine its classification capabilities, and it can then program the appropriate classification rules. Here I'm showing some examples of classification rules for the memcached stage. As you can notice, these rules are arranged in rule sets. And the semantics here are that a given message matches at most one rule in each rule set. This is based on the observation that different network functions may want a given application to classify its messages differently. So effectively, each network function can generate classification rules that reside within a rule set. What the first rule here is saying is that all get messages should belong to the get class. The second rule is saying that all put messages should belong to the put class. And class names here are hierarchical. What that means is that if you get a get message, it will match the first rule, and it will be marked as belonging to the class called memcached.r1 ruleset1.get. So effectively, we get a globally unique or a host unique class name. Yeah.
This classification also take your protocol parsing, or is that done earlier in the code?
The protocol parsing would be done by the enclave. So think of the applications operating higher up the stack. And effectively what we are saying is that the enclave should not be parsing application headers. So any protocol parsing which is application specific should be folded into classification. And what I should see as an output as the enclave is a class name that captures whatever parsing functionality was needed. There are some cases where I want to parse standard IP or TCP headers, and that part should be done by the enclave itself. So we're effectively decoupling that application protocol parsing and network protocol parsing. Does that answer your question?
So the distinction between get and put requires the application level data to have been parsed, right?
Yeah.
Initially. And that's done not at the stage.
No, that's done by the stage itself. So we are saying that memcached should be modified because memcached is going to memcached understand gets and puts anyway. It has the traffic or the buffers in those data structures anyway. So why doesn't it generate opaque class names that the enclave can then operate on, so that the enclave or the vSwitch doesn't have to reverse engineer what a get or a put looks like? So to answer your original question, application level parsing is done by the application itself, which is great if you can modify applications. So we are making a leap of faith here. We are saying that, well, actually in data center environments, you can change applications. And if you do so, the job of the network management becomes much easier, and you can express many more policies much more flexibly. Because reverse engineering all this information lower down in the stack is a very hard proposition.
So I'm just trying to figure out what that involves. So let's say I have Nginx or Apache or something.
Yeah.
I'm trying to modify. So is this an extra control socket essentially to the enclave that says, here's a well-defined get and put request coming in? So you'd augment the application with somewhere inside as parsing logic to tell the enclave through a new API.
That's what we've done right now.
Got
So
it.
the implementation, I'll talk about it in a couple of slides, is we've extended the sockets API where you'll take Apache at the right place, you'll insert the right call saying, this is a message, I'm sending a get or a put or whatever the case might be. Yes.
That makes sense.
Yeah. So these messages will trickle down the stack, and this class and metadata information will be associated with these messages, and it will trickle down with this too. And that remains true even when the message is broken down into small packets or actual network packets. And these packets then finally hit the enclave. So the enclave, as I mentioned, is the point in the network stack where we actually enforce our network functions. And it can be inside the operating system, it can be inside the hypervisor, or it can be on the programmable link at the end host. So anywhere at the network stack at the end host. This enclave comprises of two main components. First, we have match action rules. However, unlike OpenFlow, we are not doing matches on protocol headers. We're doing matches on class names, and this is because we want to leverage application level information. Second, instead of being restricted to a predefined set of actions, we are allowing for arbitrary action functions. And the second component is a runtime to actually execute these action functions. Now, as far as the execution of the action function goes, we wanted it to satisfy three main properties. First, we wanted container-based execution environment for safety reasons. So these action functions are written by trusted administrators, but we don't want to bug in an action function to crash the entire system. Second, we want to dynamically update our match action rules and these action functions. And that's pretty tricky to achieve, especially with programmable hardware, because when you want to add new code, you have to essentially reset the entire system and flush the entire system. Finally, we wanted cross-platform execution. So we want the same action function to execute on an OS-based enclave and on a NIC-based enclave. To achieve these properties, we chose an interpreter-based execution environment. So our action functions are written in a high-level language, and they are compiled to bytecode, which is then interpreted in a stack-based interpreter. As far as the actual action function language goes, our action functions are written in F# code quotations, and here's an example. I can go into the details later. Effectively, the choice of the specific DSL was mostly due to pragmatic reasons. For example, by using an F# code quotation, we get the abstract syntax tree for these action functions for free. which means that when we write in a compiler, the job becomes easier. And this is something that I'd very much like feedback on, because being systems people, we were like, okay, we need to implement this. What's the most pragmatic way of getting to where we want to go? Getting some theory behind it regarding whether we made the right design decision would be very useful.
So what have you done to the AST there? I don't quite understand. So you have, that's normal F sharp, right?
That's normal. Well, actually, you can easily transform this into F sharp code quotation. So effectively, I want you to write F sharp. I'm going to transform that into F sharp code quotation, which will give me the AST for free. So instead of needing to derive the AST, because F sharp code quotation is essentially a feature of F sharp that allows you to deal with expressions programmatically. So the yes, macros.
Right.
So effectively, the compiler, instead of compiling as a part of the program, it's going to give me an expression where the AST is available. And so I can just traverse that AST and generate the bytecode that I will just then run. And it's a purely systems decision. So in terms of implementation, we have two versions of our enclave. We have a version of our enclave that runs inside Windows Hyper-V, and it's implemented as a Windows filter driver. And we have an implementation on top of Netronome's programmable NICs. So this is the 3000 series of their NICs. They have around 40 processing cores or micro engines where you can run code natively on the NIC itself. For classification, we've extended the sockets API, and applications can actually call this new call that we've imposed to pass class and metadata information down the stack. And then we've implemented, well, now it's about 7, but these are the more interesting ones, network functions using these prototypes. So over the next few slides, I'm going to dive into the details of one of these network functions as a case study to give you a feel for what Eden can do and what the consequent performance overheads are. So this is the first example that I mentioned, a data center flow scheduling. If you remember, the goal here is to minimize flow completion time through prioritization inside the network. Now, we've implemented 3 variants of this network function. The first is baseline, where there is no prioritization, and it represents the state of the art. The second is PIAS, which is the technique proposed at NSTI, where flow priority reduces over time. And the third one is something that we call shortest flow first. This is based on the observation that if an application is cooperating and it can give you the flow size at flow startup time, instead of trying to approximate shortest flow first, you can actually just implement the policy, which is optimal in terms of reducing flow completion times. Now, for each of these network functions, we have 2 implementations. There's an implementation natively inside the kernel, and there's an implementation inside the Eden enclave. The workload here is based on a search engine, I'm sure you can guess. The implementation is inside Hyper-V, and the hosts have 10 gig network cards. And the traffic is divided into 3 categories. There is small flows, medium flows, and large flows. Typical setup used in the networking community. Now, this graph shows the performance or the average flow completion time for the short flows. And you can see, as you'd expect, that PIAS, by using prioritization, is able to reduce flow completion time by around 25%. However, the shortest flow first strategy reduces it by 40%, which again makes sense because this strategy has extra information. And this goes to show the benefit of using that extra information. Now, the thing that I actually want you to notice is that in all 3 cases, the performance of the native version and the Eden version is very similar. As in, statistically, there's no difference at all. Which goes to show that at least in terms of application level metrics, our Eden enclave is not imposing too much overhead. And the graph looks very similar when you look at tail performance. So this is the graph for the 95th percentile flow completion time for the short flows. And again, the 3 messages hold. Prioritization helps, and the Eden enclave does not impose too much overhead. And the graph also looks, if you look at, looks the same if you look at medium flows. Prioritization helps, and we don't impose too much overhead in terms of application level metrics.
Do you have intuition why Eden does better than native for PIAS?
Because we worked on this forever. Mostly because these are really they look silly, and that's why we have these error bars. It's mostly because of system reasons. Effectively, these numbers are so slow that there are other factors that are dominating. These graphs look a little bit better when we focus on medium flows, where the green is almost always a little bit above the red. They're statistically still the same, but that's why the short flows, as in we spent I don't know how much time on this because it's an anomaly. Does this make sense? So to quantify the actual CPU overheads, we looked at a synthetic workload. In this case, we have 12 TCP flows that are saturating a 10 gig link. And we are trying to quantify the CPU overhead imposed by us at the average and the 95th percentile. And we have broken this down into API overhead, which is the overhead of carrying metadata up and down the stack. The interpreter overhead, which is the fact that, well, we have the stack-based interpreter. And the enclave overhead, which is when a packet comes in, we need to look up a hash table to match the class and then execute the actual action function. And obviously, this depends on the action function being executed. But you can see that most of the overhead is dominated by the fact that we need to match on the class name and actually execute the action function.
So in this case, who does the enclave CPU get accounted to? Is it to the application, to the data center provider, or?
That's a good question that we haven't given that much thought to, but I would argue at the moment we are expecting that most network functions would be written by the data center provider. So in that case, it should be counted against the data center provider. There's an interesting research question.
Why would you think that? Just because it was written by the data center provider, right? Which is to say, if I make more heavy use of things that you provide to me, I ought to pay for them, right? Sorry, and that doesn't.
Yeah, yes. That's a very good point that I hadn't thought of. It makes sense that actually, which is given funny because I've been working in QoS where effectively I want any shared resource to be shared fairly and to be accounted for fairly. And if I were to think of the enclave as a shared resource, I want to make sure it's shared fairly and accounted for fairly in price terms or not. But actually what I wanted to mention was that there are interesting research questions when you start thinking about action functions written by arbitrary users, both in terms of what the performance implications are. And I'll come to that in 2 slides from now. I'm done here. CPU overheads are pretty low. We know how we can bring them lower through better prototyping. So I'll summarize those versions of the talk and then we'll move on to the open questions.
Yes, no, any order you want.
Okay. So in summary, 5 minutes? Excellent. So in summary, what I've told you is that 3 common requirements underlie a lot of network functions, and end hosts are a natural enforcement point given these 3 requirements. And what we've done is we've implemented an architecture that enables you to implement network functions at end hosts with minimal network support. Now, Eden relies on 2 ideas: programmable classification and application messages, and a programmable data plane with a much richer API. In terms of what we're doing right now, obviously there are a bunch of things in terms of improving our prototype, especially our runtime on top of the programmable NICs. But there are a couple of interesting questions that I wanted to highlight, and I'd love to get feedback now or later in the Beragius opinion session, something like that. So the first one is the high-level vision has always been, with our project and pretty much most projects in network management, is that human operators should specify high-level policy. Right? You should be writing a network function, the functionality that you want to achieve, assuming that there is an Oracle controller or a centralized Oracle where you could run it. You should not be concerned about whether it's implemented at the end host or at the switch or at mailbox. Ideally, what we'd like to do is we'd like to take this centralized network function or an ideal network function and automatically partition it into functionality that resides at the controller because it requires global visibility, into functionality that's transformed into classification rules because it requires application semantics, and functionality that goes as action functions into the enclave because it needs to reside on the data path. And I'm convinced that if this automatic program partitioning were to be possible, that would really open some of the benefits promised by an Eden-like architecture. Going back to your question, we have this richer API, which is great, right? We can do all these funky things. It's a much more flexible model. But a richer API means that you can impose significant overheads on the CPU and the memory. And it would be really neat if either we could bound those overheads, or in actual most cases, we actually don't want to bound them, because in some cases, you as the data center operator may want to run something which reduces performance but adds extra functionality.
Right.
And it would be great if I could expose that trade-off to you, saying that, well, actually, if you run this network function, given the expected traffic patterns, your end host would only be able to sustain 7 gigs. There is an approximate version of this network function that you can run at 10 gigs. And it's upon you to decide which one you want. And maybe this is complete sci-fi, but if that were to be possible, if exposing that trade-off were to be possible, I think that would be very, very neat.
Right.
Anyway, I'm going to stop there, and I'd be happy to answer questions and get more feedback and discuss more. Thank you.
Thank you.
Sorry, I interrupted you. You were
No, just the observation that in the Zen hypervisor, we spent about the last decade breaking up the hypervisor into lots of small interoperating components, so essentially just a real system. And so the goal of that is to do the fine-grained yet multi-tenant charging that you want to get done. So what you really want to do is, Hyper-V is roughly the same architecture, right?
Yep.
So even though it looks like an enclave, it could just be 100 virtual machines running the same on the same hypervisor, each of which is individually accounted for with shared memory and all kinds of optimizations. So there's nothing fundamental about the fact that it's run by the data center operator, I think, making it difficult to charge the other side. The interesting part of the enclave is that you could, in theory, I think, run one enclave per user.
Yep.
And multiplex at a very low level with metronomes as well.
Yeah. The only thing I'd like to be able to do is somehow bound the performance impact, right? So the way I do bounding a performance impact of VMs is that I'm just going to say, you bought a small VM, so you get a core for your VM. And that obviously offers a nice physical isolation because you can't impact. As in, you can still impact because of shared caches, but to a first order, you're isolated from other users. Now, if I have a 12-core machine or a 16-core machine and I'm having 12 cores dedicated to actual VMs and then 2 or 3 cores for the rest of the stuff, it always becomes tricky. I think I know what needs to be done. It's still not crystal clear how you do that partitioning when the underlying physical resource is shared. Does that make sense?
It does, yeah. Just don't do very much, I guess, is the answer there. Try to not complicated than somewhere else.
Yes.
Instead of a virtual machine. Yeah, that makes a lot of sense.